Hi everyone, welcome back to Chem Help ASAP. In today's video, we are going to take our molecular geometry and we are going to predict dipole moments. Now, make sure you're comfortable not only with your Lewis structures, but also with your VSEPR because we will be using both of those today. If you need a refresher, you can check out my videos on both of those topics. Now, the first thing that we are going to learn about is electronegativity. So let's get started. We define electronegativity as how strongly an element will attract shared electrons. So if we're looking at the periodic table, we can draw general trends for electronegativity. Electronegativity will increase, moving from left to right, and will decrease, moving from top to bottom. One thing that helps me remember this trend is the most electronegative element on the periodic table is fluorine. Now, differences in electronegativity means that in a covalent bond where atoms are sharing electrons, they do not share equally. So for example, here is the Lewis structure for hydrofluoric acid. The fluorine atom is more electronegative than the hydrogen atom. That means the electrons will spend more time around the fluorine atom. This gives fluorine a partial negative charge, and therefore hydrogen has a partial positive charge. The way we represent this is we draw an arrow with a positive end to the less electronegative atom and the negative end here to the more electronegative atom. We call this difference in electronegativity the dipole moment. If we were to look at carbon monoxide, here is its Lewis structure. Based on the periodic table, I know that oxygen is more electronegative than carbon. So oxygen is going to end up with a partial negative charge. Carbon is going to end up with a partial positive charge. And here is my arrow representing the dipole moment of this bond. Now, not all bonds have a dipole moment. If I take a look at the Lewis structure of nitrogen gas, there is no difference in electronegativity because I have a nitrogen bonded to a nitrogen. This bond has no dipole moment. If there is no dipole moment, we call this molecule nonpolar, which means any molecule with a dipole moment we would call polar. Let's clear the page and let's practice with some bigger molecules. Here is the Lewis structure for carbon dioxide. Based on our VSEPR model, we know that this molecule is linear. So our drawing here accurately represents its 3D shape. The question is, do these bonds have a dipole moment? Or you could say, are these bonds polar? And the answer is yes, of course. If I look at this carbon-oxygen bond, oxygen is more electronegative, so my arrow is going to point towards it. Carbon ends up with a partial positive charge. What about my other carbon-oxygen bond? It has the same thing. So this molecule has two polar bonds. Now, once we are dealing with a molecule that has more than one polar bond, our next question that we want to ask is the molecule overall polar, or does it have an overall dipole moment? To answer that question, we need to take a look at our polar bonds and add them up very similarly to how you would do vector addition. But don't panic, you don't have to have your physics to determine if these are polar molecules or not. Because I know this molecule is linear and the oxygen atoms are 180 degrees from each other, I know that the oxygen atom on the left is pulling just as much on the carbon as the oxygen atom to the right. So if you had two friends of equal strength pulling on your left and right arm, you would not move. These two vectors actually add out. Carbon dioxide is a nonpolar molecule. Let's take a look at another simple molecule. Let's take a look at water. Here is my Lewis structure. Do I have polar bonds? Do I have a difference in electronegativity between the oxygen and the hydrogen? The answer is yes. Oxygen is more electronegative than hydrogen. So this bond is polarized towards the oxygen, and so is this one. At first glance, you would say this is the same situation that we saw in carbon dioxide. We have two polar bonds, but they are basically going to add out. However, we have skipped a very important step. What is the shape of this molecule based on our VSEPR model? Well, its shape is bent. The way we have drawn it here does not represent the molecule in 3D space very well. So we need to redraw it to represent better what it looks like in 3D space. This is a much better representation of what water looks like in 3D space. Now let's put in our polar bonds. You can see now that these bonds do not add out, that actually we are going to have an overall dipole moment that looks like this. When we have an overall dipole moment, we say that this molecule is polar. Let's do one more molecule. Let's do a larger molecule, sulfur hexafluoride. Here is its Lewis structure. Based on VSEPR, its shape is octahedral. Now the way we've drawn our Lewis structure here is not very helpful to us to visualize it in 3D space. So I am going to use wedges and dashes to help. Remember, the wedges mean that these fluorine atoms are coming out of the page towards you, and the dashes mean that those fluorine atoms are behind the page away from you. Do we have polar bonds? Yes, there is a difference in electronegativity between sulfur and fluorine, so let's draw in our polar bonds. Fluorine, as we know, is the most electronegative atom. So all of my arrows are going to point towards fluorine. Now, one thing that might help you visualize better is a picture of an octahedral molecule in 3D space. What hopefully becomes more obvious in the 3D molecule is each fluorine atom, as it's pulling away from the sulfur, is paired exactly 180 degrees away from another fluorine atom. This means that all the dipole moments add up to be 0 for this molecule. Therefore, we have a non-polar molecule. It has no overall dipole moment. Just like we saw in the video, it is super important to draw your Lewis structure so that it looks like the molecular geometry predicted by VSEPR. I have gotten so many student papers back where they didn't take the time to redraw their Lewis structure, and unfortunately their dipole moments are wrong. So please be careful drawing out there.
I hope you found this video helpful, and thanks so much for watching.